Good morning, students. Last class we have seen that power stages in induction motor, how the electrical power converted into mechanical power. During this process, what are the different losses takes place in various parts of a induction motor. As we know that energy cannot be created, cannot be destroyed, but it can convert from one form to another form. Here the electrical power is given to the motor. First, in stator itself, some of the energy is utilized to generate the magnetic field, and some of the energy is wasted as a heat energy, that is called I square R losses in stator winding. Some amount of the power also wasted in the form of iron losses. Now that is in the form of eddy current losses, that is also heat losses. Whatever the remaining input minus stator losses, that is called stator output power, that is equal to rotor input power, that is flows through the air gap to the rotor. Then rotor takes P2 as a power input to the rotor. This magnetic energy generates electrical energy in rotor conductors, and it is also produced as rotor power, that we can say it the PM, mechanical power developed in the rotor. This is generated after taking the power from the stator, that is called P2, minus some losses also takes place in rotor, such as copper losses and iron losses. As we know that the copper losses depend on the I square R losses. There is a copper bars inserted in the rotor in case of the squirrel cage induction motor, whereas there is a three-phase winding wound on a rotor in case of slip ring induction motor. So we have to consider some amount of the copper loss in rotor. At the same time, the rotor has some rotor core which is also laminated, and this iron losses depend on the frequency of the rotor. The induced EMF in the rotor, the frequency is very low, that is called frequency of the rotor is equal to the S times of frequency of the stator. The stator itself 50 Hz. Under running condition, the frequency is very low due to the slip, maybe 2 to 4%. Hence, the iron losses, eddy current losses and hysteresis losses depend upon the frequency and voltage, as we know that. Hence, these losses are very less. Hence, we are going to neglect for our simple analysis purpose. So, whatever the rotor input, that is equal P2 minus this rotor copper losses, we are going to get the total mechanical power developed in the rotor, that is in the form of mechanical energy. This mechanical energy now given to the shaft, where shaft will take the mechanical load on the shaft. In between, that is we can say P out, rotor actual motor output. So PM minus P output equal to some losses. That losses may be the power is required to overcome the friction and windage losses. finally we are going to get P out. Okay, so these are the different stages already we have seen in the last class. Okay, now based on these formulas we are going to do some simple problems. Okay, so once again I am going to recollect what are the problems we have seen. So as you know that this is the 3-phase induction motor, and it will take the power as a P1 in terms of 3-phase √3 VL IL cos phi. Okay, this is the power input. Now after that some power is given to rotor. This is equal to, here what will happen, some P copper losses, P stator losses. What are the losses? So we have seen P stator copper loss, P stator iron losses. Okay, so P1 minus these stator losses, we are going to get it stator output. That is equal to, we can say this is equal to P2. So that P2 entered into rotor. This P2 entered and it develops some mechanical energy at the shaft. Okay, so mechanical energy developed at the shaft, that is equal to the P2 input and utilized for mechanical energy, that is the total mechanical energy developed in the rotor plus some rotor losses. What are the rotor losses? So here we are assuming that only copper losses. So we are neglecting iron losses. Okay, iron losses of rotor we are neglecting because the frequency is very low. Now what is happened here? The P2 is equal to the total mechanical power developed in the form of mechanical energy plus the P copper in rotor in the form of heat energy. Now from this PM, total PM, that's the total mechanical energy is developed in the motor, that is a rotor, is given to the P output, that power available at the shaft, plus some power is wasted in the friction and windage losses. So then finally we are going to that. So P out, power out, we are going to in the form of mechanical energy. Okay, mechanical energy. So what has happened? The P1 is given in electrical energy, and finally we got it in mechanical energy. What is the efficiency? The efficiency of overall motor is equal to percentage efficiency of overall motor is equal to total motor is equal to, we can write it the P output by input, output by P input, that is equal to P1 input into 100. So we are going to get this, that is equal to P out and by P in, that is equal to P1. So this is into 100. So this is a percentage of motor. Suppose I want the rotor efficiency. So we know the rotor efficiency also, the efficiency of rotor. Okay, so what is the output? Output is equal, that is equal to PM. Okay, mechanical power developed in the rotor divided by P2 input, the energy. So that is a percentage means into 100, or we can easily calculate it. Okay, these all formulas we have derived in last class. At the same time, finally, so we have derived one good formula, that is equal in terms of P2 input of the rotor is to rotor copper loss is to mechanical energy developed in the rotor is equal to, so we are going to ratio of, so 1 is to slip is to 1 minus slip. So this is a formula concluded final stage. Okay, if you know this value, so we are going to calculate any problem, a motor characteristics we can find. Okay, what is the formula? That is equal, I want suppose here the rotor. What is the rotor here? So we have the rotor. So whatever the power P1 is given, P1 we know. So what is the value here? So I want the, so P1 I know this value. Okay, so I know the P1, I know the P2 if know the this losses, stator losses. So if the stator losses known, so here what is happened? So this is a rotor input, the rotor. Okay, rotor input is the P2, rotor output is the P out. Okay, so we can say that is a, we can write, sometimes we can write it, this is a P M, mechanical output. This is a magnetic energy, this is the mechanical energy. Then if you know the input by output, we are going to calculate the percentage. Now based on this one, if you know the P2, what is the input? If you know the P1 input, that is equal to root 3 VL IL cos phi, and if you know the stator losses, that is the stator loss. So P stator losses, that's the values which we know. Then we can easily calculate it. P2 is equal to P1 minus P stator losses. Then so we are going to calculate what is the P2. If you know the P2, that is equal to, what is the P2? That is equal input. Okay, rotor input. If you know the P2, then I want the rotor copper loss. Rotor copper loss I can easily calculate it. What is the formula? And S times of P2 only. So I am going to calculate this thing. At the same time, I want to know that, so P M I want to know. So that is equal to, I can write it, so P2 minus P copper. This is the total input minus copper losses, we are going to PM, or I can write it, so 1 minus S times of P2. I am going to get this the another equation. Okay, so this is another equation. So if you know this all values, we are going to simple do the any problem. Suppose I want to know the what is the current, input current. So motor input current I want to know. So what is happen? So I want to know the current. This is if you know the input, P input is known, P1 that is equal P input. Then I want to know what is the current of this one. So current can be calculated. What is the formula? P1 is equal to root 3 VL IL cos phi. Okay, I want the IL. So IL easily calculated, that is called P1 by root 3 VL and cos phi. If you know the power factor, if you know the voltage, if you know that this one, and substituting, we are going to get the that current, whether it is connected star or we connect with the delta. First we know that this value, after that we can easily convert with the star and delta. Okay, so these are the things we have learned. Sometimes what will happen, some problems. So here is a input is given, then we are going to calculate the current. Suppose sometimes the motor output will give, suppose he will give the some HP motor, so 10 HP motor, of induction motor. So whenever this is given the nameplate details 10 HP, this assumed as a output, not input. Dear students, please remember it. On nameplate details, suppose 3-phase induction motor 10 HP, that means this is the output, not input. So you are going to calculate the current, input current based on the input, not this output. So that purpose already we know that how you are going to calculate the input current. So that purpose you are going to calculate. So you will give the, this is a output is equal to, how much is given? Output is equal, for example, 10 kilowatts motor output, for example, instead of HP. So 1 HP is equal to 735.5. So generally we can write it, that no 745.5, sometimes we can write 735 also. Okay, so whatever the value you take it, watts. So now here directly in this one, I want to know the what is the current. So I want to know the what is the input current. So here you will give the some values also. So PF you will give what is the power factor. For example, if it is not given, you take the 0.85 as a lagging power factor for induction motor. Sometimes you can give the efficiency also of the motor. So efficiency will give nearly 80% or 85%. Then based on these factors, we are going to convert. So input value. What is the input current? So here output is given. Okay, output is given. What is the efficiency? Percentage of efficiency is equal to output by input. Okay, into 100. Then output is given. What is the value is given? 10 kilowatts. Okay, 10 kilowatts is given. Now input, you don't know input, just you write it here. So input is equal to, then what is the percentage? So you given the 0.85. So 0.8. Okay, then into 100. Then you are going to the what is the some value. What is the value now? It becomes to the for example, input is called 12 kilowatts. Okay, then input is the output is the 10 kilowatts. Let us assume 0.8. What is the value? So we are going to that. Okay, some you take this one. So is given. Now based on this input current, now I am going to calculate the current now. Okay, based on the input I am going to, what is the input? You know this is nothing but P1. Simply substitute the current. I1 is equal to, so P1 is equal to by 3-phase √3 VL and cos phi. Okay, cos phi is given. Now what is happened? P1 is equal to how much is 12 kilowatts, we got it, into 10 to the power of 3 watts divided by, so √3, and VL is equal to 3-phase, that is a 400 volts, into cos phi is equal to 0.85 lakh. So by doing simplifying this one, we are going to the current, that is the input current. Okay, if given the output, it convert to the input, then find the current. This is a method. So already you have done this type of the problems in other subjects. Okay, let us do one problem in our AC motors. Okay, based on this basic idea, now we are going to do one problem. Okay, so let us do that one. Now is one problem is given. Okay, so what is the problem? A 4-pole 400 volts 3-phase 50 Hz induction motor runs at 1440 rpm at 0.8 power factor lagging and develops an output of 10.8 kilowatts. The stator loss is 1060 watts. Friction and windage losses are 390 watts. Calculate first slip, rotor copper loss, rotor efficiency, stator input and line current. Sometimes we will ask the torque also. What is the gross torque? TG. T shaft also he will ask. Okay. Now let us do this one. So once again read the problem. A 4-pole machine. So here is a one machine is given. Okay, this machine is given. A 4-pole machine, P is equal to 4-pole machine and 400 volts. Okay, 3-phase machine and 50 Hz frequency is given. Induction motor runs at a n is equal to rotor speed is given 1440 rpm. 1440 rpm is given. Okay, no problem. And at power factor, PF also is given. PF also is given. What is the 0.8 lakh is given. And develops a output. So here is a what is output is given. That is equal P out is given. P out. What is the out is given? P out develops 10.8 kilowatts power is given. P out is given. The stator loss, here also stator loss is given. The stator loss is equal to 10, that is equal 1060 losses is given in watts. Stator loss, that is called copper loss plus iron losses, both are 1060 watts. And also is given friction and windage losses are also given in the rotor. So what is the given? Losses also is given. So friction and windage losses. So how much is given? 390 watts is given. Now calculate what is asking. Calculate what is asking. First one, he asking what is the, now we can see. Now he is asking one is the what is the slip. Okay. Now second one is the rotor copper losses, P copper loss, and rotor efficiency, efficiency of rotor, not motor. So let us we calculate total motor also. Next, stator input. So that is the stator input, that means P1 is asking the P1 also, and line current. Okay, I also is I1 also asking. So these four we are going to calculate. What is the slip? What is the rotor copper losses? What is the rotor efficiency? What is the total input to the motor in the form of electrical energy? At that condition, what is the current is taken by the motor, that is the I1. This is our aim. Okay, we can easily calculate it. So what he has given is given from the side, this side, output to input we have to go. Okay, so here what he has given, so the motor, whatever this motor, okay, so is given the is rotor side. We are going to find that stator side. Simply add it. What is this one? So we have already we know that. What is that one? So here P1. Okay. So we can see that one. Okay. So what is that one? The P1. Okay. My P1 is equal to, we can write it P stator loss plus P2. Okay. Now from this one, then P2 from this one, what P2 is equal to, total input is equal to rotor P, rotor copper loss, okay, plus total energy generated in the rotor. Okay. From this one, now we are going to calculate, that is equal to, now that is a PM. PM is equal to P out plus and friction windage losses, friction and windage losses at the shaft. So this is our aim. Okay. Now you can observe what is the values is given here. Simply you can see this value is given and this value also given. Okay, P out is given. What is the value is given? So that is equal to nearly 10.8 kilowatts is given. At the same friction and windage losses also given. So by adding these two, we are going to the PM. Okay, after getting the PM, now I want to know that what is the rotor copper losses. Has the rotor copper losses given? No, I think is not given. If you know the PM, so we know the some relation. What is the relation? So based on the relation, we are going to calculate the that one. So first here, so I want to know that P2 I require to know. If you know the PM, if you know the, I want to know the this speed also is given. So I can find the slip. Then PM is equal, I can write it 1 minus S into, that is equal to P2, I can write it, that is called P2. So here PM I known. From this one given rated speeds, so is given the rated 1440 RPM, I am going to find the slip, then a substitute I am going to get it. So P2 I can get it. So I will get the P2. If I know the P2, if I know the PM, I can easily calculate the P copper losses, or I can write it simply the PM. So that is equal P copper losses is equal slip I know, and I calculated P2, here I calculated P2, then I am going to copper losses. Okay, then what is happened? I know this P2. If I know the P2 and the stator copper loss is given, add this value and this value, we are going to the P1, total power of the motor is input of the motor, we are going to get it. If you know the P1, so I can easily calculate the I1. Okay, what is the formula? P1 is equal to root 3 VL IL cos phi. Power factor is given. Okay, now P1 I am going is calculated, root 3 is constant, VL is directly is given. What is the 400 volts? I am going to cut this current. So IL I can find. Okay, now we got all values. You can see here what is required. Based on the rotor speed, I calculate the slip, and based on this one, I am going to calculate the what is the P copper loss, rotor P copper losses, and we know the rotor efficiency. What is the rotor efficiency? Rotor efficiency is equal, I can write it that what is the input, that is called PM by P2 into 100%. I am going to find the rotor. I know the PM, I know the P2, then I can calculate this also. Okay, P1 I calculated and I calculated. So everything is clear. Okay, so dear student, so will you try it? Okay, so you do the problem. Can you do? Simple, just you calculate. So given the output, everything is given. Just you have to substitute the values. Okay, let us do. I am going to the back. Now, what is this given? First, P out is given. Okay. Now, what is the P out here? P out. Okay. P out is given. What is the value? 10.8 kilowatts is given. Okay. So, here you can take some value. Okay. 10.8 kilowatts is given. Now, convert into watts. Okay. 10. That is instead by into 1000, we are going to get the 00 watts. Now, what is the friction and windage losses? Friction and plus windage losses. So, add it. So, that is equal, I am going to get what is the losses is given? 390 watts is given. So, here what is the value? We are going to get the, you are the P, here PM. PM is equal to P out plus friction and windage losses. Then I am going to get these two values added, 10800 plus 390. Okay, so then I am going to get the values. Okay, so I am going to the PM. Okay, P out and prediction of intelligence. This is the way I am going to the PM. At the same time, keep it. Then, so you better to find that what is the slip. Slip purpose, n is given. What is the speed is given? So that is equal to nearly 1440 RPM is given. I want the slip. Slip is equal to ns minus nr. Okay, that is n divided by ns. Okay, so I want the ns is required. Slip ns is equal to 120 f by p. Okay, now 120 is a constant and frequency is a 58 is given. P is the number of poles. How many poles? 4 poles. 4 ones are 4 threes are. That is equal 1500 RPM. So dear students, please remember. So here speed is n is equal 1440. Is a just above. That should be above this value, not below this value. Please remember that. So it is a 1440 RPM rotor speed, but actually the magnetic RPM speed is the RMF, rotating magnetic field is the 1500 RPM. Okay, so now based on this one, you substitute this value. Now, so ns is equal 1500 RPM. We calculated is given 1440 is given and divided by 1500 RPM. Okay, into 100%. So we are going to the percentage of slip is given. What is the value? We got it. So that we are going to get it. Slip is equal to S. We are going to S is equal to nearly so 0.04. That is a 4% slip. So S we known. Okay, based on the S we are going to get it. So already here we calculated what is the value. So that we are going to get is so 10,800 watts plus 390 watts. So we are going to get it this value by simply add it with the calculator. So we are going to 1190 watts. So that is equal to we are going to PM. Once you know the PM, once you know the P2. So what is the formula? So we know that PM is equal to 1 minus S into PM. Okay, now so 1 minus 0.04, okay, into what is the PM? We got it. So PM value is we are going to 1190, okay, into 11190 watts. Okay, so by doing this one, so we are going to get what is the value. So this is a P2. Oh, sorry, this is a P2. Okay, P2 we don't know. Sorry. So what is happened here? This is the input. This value is this is a P2, and here P2 I want no P2. So PM is given. What is the PM? 1190 watts. Okay, so we know this value. We know this value. From this one we are going to calculate the P2 value. So P2 value we are going to get is nearly, that value is equal 11656 watts. We got it. That is rotor input, we got it. So you require the rotor copper loss. So P rotor copper loss is equal to S times of P2. Okay, that is equal to, we are going to that. So that is equal to 0.04 into substitute this value 11656 watts. Then we are going to 466.25 watts. This is the copper loss occurred in the form of heat energy in the rotor. Okay, now you know the P2 directly. Now P2 is given, rotor input is given, rotor, that is the stator output is given. This is the stator output. Stator losses also is given. Then P1 is equal to stator input is equal, that is equal P2 plus stator losses. Okay. So, P2 we know. What is the P2? So, already we know this this known. So, substitute this value, that is called 11,656, okay, plus, and stator copper loss is 1060 is given. So, we are going to get nearly 12,716 watts. P1 is known. Okay. Then based on the P1, I am going to calculate current. So, that current is equal, P1 is equal to root 3 VL IL cos phi. I want to know this value. Then IL is equal to P1 divided by root 3 VL cos phi. Okay. Now, substitute the value. What is the P1? We calculated just now. So, 12716 divided by root 3, this is a constant, and voltage is 400 is given, and power factor is called 0.8. Simple do it, then we are going to get it nearly 22.94 amps. It will draw from the supply. Okay. This is the line current. So, we know the line current. So, whatever he asked, so everything is we know. Okay. So, now we calculated, you can see here. Now, what is he asking? Everything we calculated based on these values. Okay. So, this is the problems. Now, suppose sometimes he will ask what is the torque. If we ask the torque, how we are going to calculate the torque? Simply torque PG. Suppose we want to ask the torque. So, you want the so TG is we are going to ask. Gross torque is so we are going to calculate the TG. We know that two formulas. TG can be calculated by two methods. What is that one? The power is equal to the torque into omega. Okay. So, I want to know that TG, I can write it two forms. TG is equal to, in terms of the TG is equal P by omega. So, I want that you can write it P in terms of Pm by, that is equal to 2 phi n, okay, by 60. I can write it this equation, or I can write it another equation also, the P2 by 2 phi ns by 60. So, by substituting these values, we are going to get the gross torque developed at the motor also we can calculate. Okay. So, this is another. Suppose you want to ask the efficiency. So, your rotor efficiency is asking. Okay. What is the rotor efficiency? Efficiency of rotor is equal to, what is the that is equal Pm by output by P2, okay, into 100 percentage. So, Pm we known, P2 we known, we are going to calculate this value. Okay. What is the Pm is given? The rotor efficiency. So, rotor efficiency, that is equal, we given the what is the Pm? I can write this value, or we know that. So, Pm by P2. So, what is the formula? Pm by this, so we can write the Pm is equal to 1 minus S into P2. Okay. So, otherwise I can calculate. So, here I want to know, this is a Pm is a input, this is a output, this is a input, this is a output, rotor. Okay. Then Pm by P2 is, can write it 1 minus S. So, 4% slip, I can calculate the percentage of efficiency of rotor, or I can calculate from this also. Okay. Pm by P2 into 100, otherwise in terms of slip also I can calculate the percentage. So, what is the percentage I am going to get here? 1 minus 0.04. So, I am going to get nearly 96%. Rotor efficiency is the 96%. Suppose I want the overall machine efficiency, then overall motor efficiency is equal to, that is equal P out by P in. So P out is given 10, that is a 800 watts divided by P in. We calculated the P in. Here also already we got it. What is the value P in? So P input, the stator input. So we are going to get that value is equal nearly what is the value? 12716 watts. So we are going to into percentage multiply 100. Then we are going to the what is the efficiency. Okay. So these are the some simple manipulation of problems. Please do the remaining all problems. Okay. So dear students, so here I am going to explain how to use this our derived equations. Okay. So please go do the remaining problems. Okay. So let us close this class in this one. Okay.